Hello. Yes, food and dairy. Fall 2020. I just wanted to touch in with the class, and there's a couple things I want to point out about our sauerkraut fermentation project. As you know, we had the week off, so I went and tested T2. That's 2 days from when we set it up to start with, and then I ran 4 days, which I'm calling T4. Now, we sent you a paper, and this paper, I hope you got it. It gives you an overview of one of the most important initiators of fermentation, leuconostoc. And this is just for your information. It's a long paper, but at some point we're going to have a lecture on lactic acid bacteria, but let's just talk about leuconostoc for a second. It's usually the initiation of most bacterial fermentations. It's vegetables, milk, whatever it is. This organism usually is the boost of the fermentation. And it's unique in the sense that it produces a very characteristic colony when you treat a media that contains high sucrose. So this organism, it has an enzyme that can take sucrose, which is a disaccharide, and convert it into dextran, which is a polymer, sort of like starch. You remember starch, 2 moles, is just monomer is glucose, except this dextran is made a little different. It makes, if you remember the chair form of glucose, carbon number 1. So if you want to make a disaccharide, you're going to make a glycosidic bond between carbon number 1 of one monomer and carbon number 4 of the second monomer. It's called glycosidic bond. Dextran is different. It can form a bond anywhere from C1 to C2 to C3 to C4 to C6. And that's the difference between dextran and starch. But it turns out that dextran has a big important factor in that it's used in chemical reactions. It's used as a stabilizer in all of our cheeses. It's used as a plasma substitute. So you can people actually make money growing this and selling the dextran. And now we want to take a shot of this. Since I'll introduce you to dextran, I ran a couple. Let me see which one I want to use. All right, let's do this one. So there's 2 different organisms on here, but the one I want to highlight is this dextran. This was this big old slab. This was a T, we'll talk about dilutions later. This one is a -4 dilution, and it's on growth media here is tomato juice agar. You don't have a lot of sucrose in this, but you still got, you can see they're building the typical colony from this. Now, I also have something, and this is, if you can move over here, this is a medium, and it's T4. This is a -3, and if I turn this over, you're going to notice that, holy smolies, you can't see. Look at it produced so much dextran. Look at the top of this. That's all dextran. So when you grow leuconostoc using sauerkraut, it will produce about 6 grams per 100 mLs. It is a wad. Look at all that stuff that fell off this and onto the lid when I inverted it. And this one did the same thing. It's so slimy that I can't hardly see. You got the same thing there. Huge amount of dextran. This is just a unique thing, so that's the only reason I'm showing it to you.
And that's grown on sucrose media.
That is real sucrose. So you're knocking. Now, the other purpose of this video is you have online from summer 2020. We videotaped the sauerkraut project. And in that one, we showed you some numbers, but the difference here, in that one, we incubated the summer ones at 18 degrees. Some reason or another, we did these at 21 degrees. So the 2-day and the 4-day don't match up at all. And we're going to have a lecture on environmental tolerances so you can learn what governs how fast something grows. So in this case, we're getting large numbers. In fact, it looks like sauerkraut's done, because here's two chemicals we use to do it. We use pH as a guide for how much acid is produced, and total acid. We've already up to 4%
Total lactic
total
acid.
acids, and that means nothing's great. It's done. So we're finished with this one now. Okay, the second part I want to talk about, because we're talking about growth at 21 or 22 degrees versus 18 degrees. Well, this is a shot of EMB. This is fecal coliform. Somewhere on your slides that I presented with you already, there is some lactic acid organisms in gram-negative bacteria. And this is a shot of this is EMB. It selects for gram-negative organisms like E. coli, Klebsiella, and stuff like that, and it's different strains of it. So at T2, that's 2 days, these coliforms are still around, and a lot of them. So when I measured it at T4, you can see that we're not getting any coliforms. They have died out. That whatever's growing back there is not gram-negative. So the pH and the acid is knocking out what we don't want, which is the coliforms. And then another thing that we found, this is a T2, and this media is for lactic acid bacteria. But when we find here on T2, that's 2 days of incubation. This is a -2, 1 to 100 dilution. What you're seeing here is all yeast, except the little tiny ones in the background. All of these colonies you see here at T2, the yeast are still active at 2 days. If we look at the same thing on T4, the yeast are gone. The acid has eliminated them and knocked them out of the picture. So far, all we got in that jug now is going to be your basic lactic acid bacteria.